Okay, we're going to talk about nth roots today. So we're really familiar with our radical symbol for a square root. That's something they've used for a long time. So we implicitly have a 2 in the radical there, which means what we're asking for is if a is the square root of x, that means that a squared equals x, or a times a equals x. That's what that means. That's our notation. If I have a cube root, so again, the 3 under the with the radical sign, it means that a to the third power equals x, or a times a times a equals x. So the cube root of 27 is asking for a number that, when raised to the third power, gives you 27. So that's going to be 3. And the reason that works is 3 to the third is 27th, or if we took 3 to the third equals 27, and we took the cube root of both sides, the cube root of 3 to the third is 3, and gives us the cube root of 27. So different ways to think about the same thing. We're going to expand this and just look at if we have any root that we want, not 2 or 3, but n could be 5, 6, whatever we want as we go through this. All right. We have to first off define what's called the principal root. So if I take my general setup, so where n is the index, the radical is our squiggly line thing, and the radicand, the thing under the radical, is our value that we're looking at. The nth root of something is how we read that whole expression. If n is positive and is even, there are going to be positive and negative roots. So, for example, if we look at if y squared is 36, y could be 6 or negative 6. Well, that's a problem when we're dealing with functions, because if I want to look at an inverse, I want a one-to-one mapping. I want one thing in, one thing out. I don't want two things out. It won't pass my vertical line test, so it will no longer be a function. So we define something as where that's the true mathematical expression, plus or minus root 36. I'm only going to take the positive value, which is we're going to define as the principal root. So it's defined as the principal root. From here on out, we're going to look at that value and keep it together, and only take the positive one when we're looking through this. A lot of what we're going to spend time is simplifying these square roots into things that are easier to break down, so different chunks. So our goal is to get something as the square root of something squared, because those are inverse operations, and we'll just be left with what's in the parentheses. Same thing with number 2. We want to look at, our goal is to get it as the fifth root of something to the fifth power. So if we run through the math of it, and I expand everything, we can see with the first one, I got it into a form where it was a square root of something squared. So 4 is 2 squared, b to the 6th is b cubed squared, and x to the 4th is x squared squared. And those two values undo each other, and I'm left with 2b to the 3rd x squared. When I look at the next one, where I have the fifth power, well, if I look at 125, there's no way that I can do that where I can break it into an integer that's to the fifth power. So it's left as the fifth root of 125 times the fifth root of x squared to the fifth, which is x to the 10th. Well, those fifth power and fifth root undo each other. I'm left with x squared times the fifth root of 125. That's as far as I can take that one and give me my exact answer. All right. We have what's called the product property of our exponents here. So if a and b are greater than 0, and that's a key component, because when we had our imaginary values, we couldn't do this. And I have the nth root of a times b, that's equal to the nth root of a times the nth root of b. And that's a property that we're going to use to break these up as we go down the road. We also have a similar quotient property. If a and b are greater than 0, then the nth root of a divided by b is the nth root of a divided by the nth root of b. And we'll use that property for something called rationalizing the denominator. So when I have a value, when I have a fraction and I have a square root in the bottom, we don't leave it with our radical in the bottom. So this is the square root of 3 over the square root of 2. I need to get that root 2 out of the bottom. And the only thing I can multiply by without changing the value is 1. So somehow I have to multiply by 1. And the way I'm going to do that is to multiply both the top and the bottom by the same thing. And in this case, I'm going to be root 2. So I'm going to get root 3 times root 2, which is root 6. And then root 2 times root 2 is 2. So the reason why I multiply by root 2 is because now we've gotten rid of that square root in the bottom. So I've rationalized the denominator. I get root 6 over 2. If I have something like this where I have a square root of variables, I need to again multiply by something on the top and the bottom so that the square root goes away. And my goal is to get b squared on the bottom. If I get b squared on the bottom, I've gone away with I have no denominator. I'm sorry, I have no square root in the denominator. So the square root of b, if I multiply through on both of those, that's going to give me the square root of a to the fourth times b over the square root of b to the fourth, which gives me my value of a squared root b over b squared. Now that was quick. We're going to take a more difficult example in a minute to look through this, but our goal is to somehow undo these square roots or cube roots or whatever they are and get rid of them in the bottom. So if we have something, this is from our book, and we're given the fifth root of 5 over 4a, and if I'm looking at this and I'm going through the book's example, it says, okay, got it. They broke up their square root using the quotient property, makes sense. And then their next step is to what they call just rationalize the denominator. And they don't have any explanation as to how this is working. And so that can be frustrating. You don't know what's going on, and you might be tempted to throw the book out the window. We want to try to avoid that and look at how did they do this. Did they just guess and check and hope that they got something to work, or did they actually have a process in mind in terms of how they got from one point to another? So let's look at it a little bit more closely. All right. So I break it up with the quotient property just like they had, but I'm going to look at everything in terms of exponents. So instead of 4, I'm going to write it as 2 squared, and instead of a by itself, it's a to the first power. And the reason I'm doing that is somehow I want to get things to the fifth power, because if I get them to the fifth power and take the fifth root, that leaves me with the value, my base in terms of what my power is raised to. So let's look at, we want to get to that point. That's my goal, because then I'm going to be left with 2a on the bottom there when I undo those fifth powers. So if I have two 2's, well, if I have an exponent of 2 already on my base of 2, then I'm going to need, right, I'm going to need to multiply by 2 to the third, because those 2 and 3 will add up to 2 to the fifth. And if I have a to the first, I want to get to a to the fifth, I'm going to have to multiply by a to the fourth. Well, if I want to not change the value, if that's what I put on the bottom, that's what I have to put on the top. And so now we can see where that leap has come from, where we get the 8a to the fourth that they had before in our example. So what we're left with is the fifth root of 40 times a to the fourth. We can't touch that, all over 2a. So we've rationalized the denominator. We have one more type that this might look at. It's similar to our imaginary numbers from before. If I have rational and irrational numbers where I'm adding them together, we are going to multiply by what's called the conjugate. So we are going to, instead of 4 minus root 5, we're going to multiply by 4 plus root 5 over 4 plus root 5. We run through our math, and we just multiply it out. So we FOIL it, and on the top we get this mess. On the bottom, though, we see what happens is our 4 root 5s are going to cancel, and the root 5 squared is going to cancel in terms of the square root and give me just 5. So I get this on the top if I combine my terms, and on the bottom I get 16 minus 5, which is 11. So again, I've rationalized the denominator. I have something that no longer has a square root in the bottom. And just as an aside in terms of why we do this, it's kind of a holdover from previous times when we had no calculators and we had just a table of values. And so it's easier to multiply by these decimals. Let's say you had root 3 is 1.732. And instead of dividing by 1.732, it's easier to multiply by it. And so you would rationalize the denominator so you don't have anything where you're dividing by some weird fractions. Instead, you have integers down there, and it makes it easier without a calculator. So it's kind of a holdover from things past, but it's still a standard within our mathematical discipline so that we see those denominators don't have any square roots or radicals on the bottom.